conditions will keep that rain away from the KNC Visitors Complex. We can run in rain, we just can't run when there's lightning. We started our competition today rather than tomorrow, which was our original plan, in order to alleviate some of the concerns with the weather forecast that we've got planned. In this camera view, you can see the students from Utah on the left and the students from Minnesota on the right in the control room getting ready for this run. This competition is a mining competition. We are pretending that these robots were just dropped off of a lander on the surface of the moon, or we can pretend they're on the surface of Mars for that matter. And their task is to get past the obstacle field, which includes large boulders and craters that some of the robots can't drive through and will need to drive around. Some of the robots can drive right through them though. Then they have to get to the digging area, which is designated on the video screen there by a yellow line in the sand. Once they're in the digging area, they're allowed to excavate or dig up as much of this crushed volcanic rock as they can. The point this year is to go as deeply as possible. These robots need to go possibly around 12 inches deep before they get to the gravel that we have hidden underneath the topsoil, and that gravel is worth points. The topsoil is not worth any points this year. So it's a different game this year than we have had in the past because the rules have changed. The reason we did that is because the gravel is simulating icy regolith or frozen water under the surface, and that's the resource that we're going to be needing to excavate and mine on the surface of the moon or on the surface of Mars someday in order to support a human colony and to be able to live off the land while we're there. Because we can turn that icy regolith, we can turn ice into water, we can turn water into liquid hydrogen and liquid oxygen for rocket fuel. On Mars, we can also take carbon dioxide out of the atmosphere and combine that with hydrogen and oxygen and end up making methane and liquid oxygen. Only 2 minutes remain in the setup time for University of Minnesota Twin Cities, a rookie team. Now, I tend to point out the rookie teams, but to be fair, each year when a team returns, they could be a whole new team. They could have a bunch of students that graduated and are long gone, and they have to start over from scratch. Hopefully in the minute and 20 seconds that remain in the setup time, hopefully the Minnesota team is able to get their robot working properly. I'm not sure if they're troubleshooting or just using every bit of time that they have. Now, some of these teams in this competition have fully autonomous robots where the students in the control room just hit a go button and everything happens autonomously. They get extra points for that. There's a lot of points given to teams that run fully autonomously for 10 full minutes. It can be difficult for us to tell which teams are running fully autonomously though. All right, by the body posture, it does look like both teams are ready to go. The judges are going to put the final touches on the arena as they escort the students out of the arena. The students that just put the robot into the arena are not able to communicate during the run with the students that are in the control rooms. Those control rooms are completely enclosed. They can't see their robots other than looking at the screens in front of them to see data that's coming from their robot or to see two camera views that we're providing them. And we are going to start in 3, 2, 1, mark. And Minnesota Robot has moved immediately and it's in motion. And we're waiting for some motion from the Utah side. Okay, we have motion from the Utah side also. I see some of the wheels turning. That's Minnesota on the screen right there with that front-mounted bucket drum system on the end of an arm, and that arm can rotate down and push those digging buckets down into the dirt. This is the Utah robot. It has 3D printed buckets on a bucket ladder system. And Minnesota, just like that, has made it to the digging area. No problem. Those wheels on the Minnesota robot, those are 3D printed wheels, and then they coated them with rubber. And that seems to be a good decision. They didn't have any trouble making it through the obstacle field. Now we need to see the spinning bucket drum digger on the front of that robot start to spin up. And you see the light-colored conveyor belt just to the left of the bucket drum system. As that bucket drum spins, it dumps the dirt or the regular simulant onto that conveyor belt. There you can see it moving. That's Utah. We really like to see all 4 wheels moving. Utah has a lot of 3D printed parts. You can see the motor covers underneath that robot are actually 3D printed too. And you can see a red and white mesh on the Utah robot, inside the Utah robot, that actually holds the collected. Wow, that Minnesota robot is really digging deep. These robots need to dig deep in order to score, and this Minnesota robot definitely is doing that. On the left, the Utah robot, I was saying the mesh that is there to collect the simulated regolith, that's actually partly 3D printed too. The team really took a lot of effort into 3D printing a lot of parts. And Minnesota, I'm not sure it can get any deeper than that. That is a really deep dig right there for Minnesota. That's a powerful robot. The trade-off for that though is it might be a heavy robot. And so that can actually be a little bit of a point disadvantage if your robot is super heavy. But if the fact that your robot digs so much more than the competitors, if that offsets the minor point disadvantage that you get by being a heavier robot, then that's a design decision that is a smart design decision. All of these teams have a lot of different decisions to make. They have to make decisions on the weight of their robot. They have to make decisions about the data that they're going to use in the control room, whether they're going to be autonomy or not, use autonomy or not. They have even more fundamental decisions like, do we use wheels or tracks for our locomotion? Which is going to do better, which is going to perform better in this interesting material which is made out of crushed volcanic rock. 5.5 minutes remain in this 10-minute run. The first of hopefully 2 runs for both of these teams. Now Minnesota is going to do some more digging, it looks like. They're going to go ahead and use as much time, maximize the digging time instead of going back and forth and wasting time in the middle. The Utah robot on the left, they actually have 3D printed wheels also, but the Utah robot's wheels are actually 3D printed rubber instead of like a hard plastic. They actually 3D printed their wheels using a rubber material. Now we're seeing a good close-up there at the Minnesota robot digging. The students in the control room don't have this view, and so they're not able to see as well as we can see. I haven't seen their conveyor belt move in a while, and it appears that as those rotating buckets fill up, they're not able to spill out onto the conveyor belt because it's gotten backed up, which is why you see the buckets emptying out onto the ground. So there may be a problem with the conveyor belt system. We did see it move earlier, so it did work for a while. Let's see if they can get the problem solved in the next few minutes. Just under 4 minutes remain in this run for both of these teams. Utah on the left and Minnesota Twin Cities on the right. You can see the Utah students having a conversation about what their situation is. The Minnesota students actively working in their robots. And looks like the Minnesota robot is backing up to the hopper. Let's see if they can get that conveyor belt to run and dump the material that's currently sitting on it into the hopper. You can see on this view, you can see cameras enclosed in plexiglass boxes. There's all of the electronics on this Minnesota robot are sealed very well, it looks like. Okay, they've got a mechanism that's raising. That's actually the dump, the onboard dump bucket, the onboard hopper that should have been filled up with the simulated regolith material, but it seemed like the conveyor belt wasn't working, which should have been transferring all that material into that onboard basket. So even though the team probably knew that basket was empty, they went ahead and went through the motions. Because none of these teams have had a practice session. We have basically canceled all practices in order to maximize our chances of being able to run all of the teams through 2 cycles, given that there's a good chance that we will have some thunderstorm delays later on in the week. Minute 20 remaining. And it doesn't look like Minnesota Twin Cities was able to deposit anything onto the hopper, but they do have some experience and knowledge that they didn't have before, and so hopefully they'll be able to take this robot back into the pits, make some minor corrections, and come back strong for their second attempt later on in the week. This is the 9th annual NASA Robotic Mining Competition. Hopefully we'll be able to interview some of these team members as they come out of the control room in the next few minutes and be able to glean some information